For our first expression at t equals 1 millisecond, one would evaluate the ratio of t over tau as 1 over 3, or 1/3, yielding a value of roughly 8.6. If we evaluated this expression at 4 milliseconds, the ratio t over tau is 4 over 3. Ultimately, we attain a value of roughly 3.2. For our second expression, evaluated at 500 microseconds or 0.5 milliseconds, the ratio t over tau is a value of 1/4. Ultimately, at t equals 500 microseconds, y2 of t is roughly 5.3. We follow a similar procedure when t equals 1.2 milliseconds, where the ratio of t over tau is approximately 0.6. Ultimately, y2 of t at 1.2 milliseconds yields a value of approximately 10.8. Let's try this in reverse. Given known y values, we can also solve for time values that satisfy these conditions. Allow me to demonstrate. Consider an occasion in which we know 6 times e to the negative t over tau equals 1.7. Additionally, we know tau to be 5 milliseconds. At what time value is this condition true? Substitute tau equals 5 milliseconds into our equation. We're left with 6 times e to the negative t over 5 milliseconds equals 1.7. Divide both sides by 6. We're left with 0.283 equals e to the negative t over 5 milliseconds. Take the natural log of both sides. We're left with negative 1.261 equals negative t over 5 milliseconds. Multiply both sides by 5 milliseconds and get rid of the negative signs on both sides. We're left with t equals roughly 6.3 milliseconds. Consider a different occasion in which we know 6 times 1 minus e to the negative t over tau happens to equal 2. Additionally, we know tau to be 5 milliseconds. At what time value is this condition true? Again, substitute the constant tau into the equation. We're left with 2 equals 6 times 1 minus e to the negative t over 5 milliseconds. Divide both sides by 6. Subtract 1 from both sides. Get rid of the negative sign on both sides. Take the natural log of both sides. Multiply both sides by the constant tau, in this case 5 milliseconds. Get rid of the negative signs on both sides. We're left with t equals approximately 2 milliseconds. Let's see if you can try these example problems on for size. Our first problem asks us to solve for at which time the function 12 times e to the negative t over tau equals a value of 7.5, where tau happens to have a value of 3 milliseconds. Our second example problem is asking us to solve for at which time the function 24 times 1 minus e to the negative t over tau obtains a value of 19. In this case, tau is assumed to have a value of 2 milliseconds. By all means, pause the lecture and see if you can try this on your own. If you're tracking, you should have obtained the following values. To solve for the first time, we need to divide both sides by the constant 12, and then take the natural log of both sides. Then we multiply both sides by the constant tau, in this case 3 milliseconds, and get rid of the negative signs on both sides of the equation. We're left with a time value of approximately 1.4 milliseconds. To solve for the second desired time, we need to divide both sides by the constant 24, and then subtract 1 from both sides. Then remove the negative sign from both sides of the equation and take the natural log of both sides. Then we multiply both sides by the constant tau, in this case 2 milliseconds, and get rid of the negative signs on both sides of the equation. We're left with t equals approximately 3.1 milliseconds. The constant tau might initially seem like troublesome mathematic baggage. However, differing tau values can influence the shape of our curves as functions of time. Allow me to demonstrate. Tau is known as the time constant, and we'll learn in later lectures tau is determined by specific electrical properties of the circuit under consideration. As we demonstrated, the ratio t over tau influences to which negative power e in our function of interest is raised to. Consider the plot of the general purpose decay and growth functions including tau, where y1 of t equals a times e to the negative t over tau, and y2 of t equals a times 1 minus e to the negative t over tau. It should be absolutely no surprise that they look like this. The decay function y1 of t starts at a and drops to 0. The growth function y2 of t starts at 0 and grows to a. Notice both functions raise e to the negative t over tau, rather than some single x value as we did earlier in this lecture. If you want to, you can think of the ratio of t over tau, i.e. the fraction inside the bubble, as that single x value. Thinking of these expressions in this manner allows us to rather quickly plot specific horizontal and vertical values. Consider this pair of expressions. In both occasions, we know tau to be 500 microseconds. At t equals 0, the ratio of t over tau equals 0, and y1 of t is 8, y2 of t is 0. At t equals 500 microseconds, the ratio of t over tau would be equal to 1, and y1 would be 0.368 times 8, or roughly 2.9, and y2 would be 0.632 times 8, or roughly 5.1. At t equals 1000 microseconds, or 1 millisecond, the ratio of t over 2 would be equal to 2. y1 would be 0.135 times 8, or roughly 1.1, and y2 would be 8 times 0.865, or roughly 6.9. Other whole number ratios of t over tau yield immediately identifiable results. Can you dig it? The ratio of t over tau is kind of like a single x value. Everything interesting happens between 0 and 5 tau. This is super handy when it comes to plotting these curves at different tau values. For example, consider this pair of expressions where tau is no longer 500 microseconds, but rather shorter 250 microseconds. These are the same expressions as previously, only our time constant tau is half that of our previous time constant. As you might expect, things happen twice as fast. At t equals 0, y3 equals 8, and y2 equals 0. When t equals 250 microseconds, the ratio t over tau is now 1. y3 is 2.9, and y4 is 5.1. At 500 microseconds, y3 is 1.1, and y4 is 6.9. Again, close inspection of these values for whole number ratios of t over tau should yield immediately identifiable characteristics. We're transitioning through the same values as previously, only it's taking us half the time to do so. Compare the plots of these same functions when tau is 250 microseconds with our previous plots when tau is 500 microseconds. Importantly, note that these plots are using the same time scale. As we'd expect, both sets of functions restrict themselves to a y range between 0 and 8. Only the set with a smaller time constant of 250 microseconds makes the transition twice as fast as the one with a larger time constant. Can you dig it? 0 and constant a, in this example 8, still define the upper and lower bounds of both functions. However, the time constant tau either compresses or expands these functions on the horizontal axis as a function of time. The function with a larger time constant of 500 microseconds takes 5 times 500 microseconds, or a full 2.5 milliseconds to reach their final values, whereas the function with a smaller time constant of 250 microseconds takes 5 times 250 microseconds, or 1.25 milliseconds to reach their final values. For those not readily seeing this, consider yet another illustrated example of tau's influence on the shape of these curves. Consider these pair of expressions where tau is no longer 500 microseconds nor 250 microseconds, but rather a much longer 1 millisecond, or 1000 microseconds. These again are the same expressions as previously, only this time our time constant tau is super big in comparison to our previous analyses. As you might expect, things happen twice as slow. Evaluations at times where the ratio t over tau yield a whole number yield identifiable results, only the transition is now taking much longer. Compare the plots of these functions when tau is 1 millisecond with those of our previous plots when tau is 250 microseconds and 500 microseconds. As we'd expect, all sets of functions restrict themselves to a y range between 0 and 8, only the set with a larger time constant makes the transition super slowly, where the full transition in either scenario takes 5 time constants. Again, can you dig it? 0 and constant a, in this example 8, still define the upper and lower boundaries of all functions. However, the time constant tau either compresses or expands these functions on the horizontal axis as a function of time. In summary, smaller time constant, more rapid; larger time constant, less rapid. Regardless of the time constant, a function makes a full transition in 5 time constants. If you're up to the challenge, see if you can mentally plot the following functions in the same time scale from t equals 0 to 20 milliseconds. Again, just mentally plot this. Don't feel you need to waste your time with specific numbers. Long story short, think 5 time constants out for each function. If you are one of those folks that has to do everything the hard way and calculate each individual step, make it easy on yourself by considering only occasions in which the ratio of t over tau is a whole number, as in 0, 1, 2, 3, 4, and 5. Our first function set is y1 of t equals 24 times e to the negative t over tau, where tau is assumed to be 2 milliseconds. y2 of t equals 24 times 1 minus e to the negative t over tau, where tau is again assumed to be 2 milliseconds. Our second function set, y3 of t equals 24 times e to the negative t over tau, where tau is assumed to be a longer 4 milliseconds. y4 of t is 24 times 1 minus e to the negative t over tau, where tau is again assumed to be a longer 4 milliseconds. Which function will win and who will be left behind? By all means, pause the lecture and see if you can do this on your own. If you're tracking, your plot should look something like this. y1 of t goes from 24 to 0 in a span of 0 to 10 milliseconds. And y2 of t goes from 0 to 24 in a span of 10 milliseconds, where these 10 millisecond spans represent 5 time constants, each time constant being 2 milliseconds. Not a lot changes for y3 and y4, although they do take a lot longer to make the same transition from 0 to 24 and 24 to 0, given the larger time constant tau of 4 milliseconds. y3 of t also goes from 24 to 0, only takes a longer time span of 0 to 20 milliseconds, and y4 of t also goes from 0 to 24 in a span of 20 milliseconds, where again 20 milliseconds represents 5 time constants, where each time constant for this function set being 4 milliseconds. Again, the time constant tau influences the compression or expansion of these transient functions on the horizontal time axis. Functions with smaller time constants make the same transition more rapidly, whereas functions with larger time constants make the same transition over a longer time period. Let's quickly check your understanding of this concept before we move on. Consider another set of exponential decay and growth functions modeled as having transitions between 0 and 12 or vice versa. The first set makes a complete transition in 150 microseconds, an extremely rapid, abrupt transition. The second set, in contrast, makes the same transition over a relatively relaxed time span of 500 microseconds. Which set has a smaller time constant? Which set has a larger time constant? Obviously, the first set makes a quicker transition, so the first set obviously has a smaller time constant. And the second set, identified with the slower transition, has a larger time constant. The somewhat harder follow-up question is this: what are the time constants for these two sets? If you're struggling, here's a hint. As we previously demonstrated, these functions make a transition between x equals 0 and x equals 5. Think 5 time constants out. If you're tracking, you should have arrived at these conclusions. Given the first set makes the complete transition over a span of 150 microseconds, this represents a span of 5 time constants. 150 microseconds divided by 5 yields 30 microseconds. Similarly, given the second set makes the complete transition over a span of 500 microseconds, this still represents a span of 5 time constants. 500 microseconds divided by 5 equals 100 microseconds. While we're on the subject of time constants, allow me to draw your attention to an expedited analysis technique. The general purpose decay function, a times e to the negative t over tau, and the general purpose growth function, a times 1 minus e to the negative t over tau, also have general purpose plots if one uses increments of tau on the horizontal time axis. Really, the only quantities the user needs to be aware of is the constant a and the time constant tau. The constant a forms the upper and lower bounds of each function. The smaller time constants mean one is zoomed in on the horizontal scale, whereas larger time constants mean one is zoomed out on the horizontal scale. One can use these general purpose plots to accelerate the analysis of transient functions. Consider these two functions. y1 of t equals 16 times e to the negative t over 5 milliseconds, and y2 of t equals 16 times 1 minus e to the negative t over 5 milliseconds. Our constant a, forming our upper and lower bounds for each function, is 16. Our time constant for both functions is 5 milliseconds. 5 milliseconds represents one time constant. 10 milliseconds represents 2 time constants. 15 milliseconds represents 3 time constants. 20 milliseconds represents 4 time constants, and finally 25 milliseconds represents 5 time constants. In summary, y1 of t goes from 16 to 0 in 25 milliseconds, and y2 of t goes from 0 to 16 in 25 milliseconds. If you think about it, it's really formulaic. All you need to know is the start point, the end point, and the time constant. By now, you should be getting a good feeling for the general purpose decay and the general purpose growth functions. You might even be getting bored of them by now. I hate to break this to you, but as useful as these functions are, they don't cover all analysis scenarios, and sometimes more complicated conditions present themselves. A frequent complication might be a scenario in which the general purpose growth function does not grow from 0 to some single constant value a, but rather between some initial value I'll call ai for initial to some final value I'll call af for final. Luckily, a more comprehensive growth function accounts for not only this more complicated scenario, including an initial value, but also for the general purpose scenario from 0 to a. Did I just bait and switch you? Yes, I did. But trust me, you would have freaked out if I showed you this more comprehensive growth formula earlier in the lecture. I promise, this is the last curveball I'll throw you this lecture. A more comprehensive growth function might look something like this, where y of t is equal to af plus ai minus af times e to the negative t over tau, where ai is the initial value and af is the final value that might be achieved if the function was allowed to progress for a time span of a full 5 time constants, whatever that time constant might be. Like I said, the more comprehensive growth function not only accounts for a more complicated scenario involving an initial condition, but also for the basic growth function we previously discussed. Consider growth from 0 to 16 over a time span of 25 milliseconds. This can be modeled using the general purpose growth function as y of t equals 16 times 1 minus e to the negative t over 5 milliseconds. Again, the growth function reaches the steady state value of 16 in 5 time constants. 25 milliseconds divided by 5 means it has a time constant of 5 milliseconds. If we were to use the more comprehensive growth function, we can similarly model the same behavior as having an initial value, ai of 0, and a final value, af of 16, also with a time constant of 5 milliseconds. Substituting these values into the more comprehensive growth function yields y of t to be equal to 16 plus 0 minus 16 times e to the negative t over 5 milliseconds. 0 minus 16 is minus 16, which leaves 16 minus 16 times e to the negative t over 5 milliseconds. Factoring out the 16 yields 16 times 1 minus e to the negative t over 5 milliseconds, the exact same formula we obtained using the more comprehensive growth function. Like I said, the more comprehensive growth function also accounts for the general purpose scenario. Since the more comprehensive growth function works for both scenarios, my advice is to use only the more comprehensive growth function in the event you're presented with a more complicated analysis scenario. Speaking of which, let's examine a more complicated analysis scenario. Consider an occasion in which growth starts at an initial value of 4 and then reaches 16 over the span of 25 milliseconds. Using the more comprehensive growth function, we can model this behavior as having an initial value, ai of 4, and a final value, af of 16, also with a time constant of 5 milliseconds. Substituting these values into the more comprehensive growth function yields y of t to be equal to 16 plus 4 minus 16 times e to the negative t over 5 milliseconds. 4 minus 16 is minus 12, which leaves 16 minus 12 times e to the negative t over 5 milliseconds. Compare and contrast the plot of growth from 0 to 16 in brown with that of growth from 4 to 16 in green over the same time span of 25 milliseconds. As one might expect, growth from 4 to 16 needn't be as abrupt as growth from 0 to 16, given it's got a head start of 4 and only exhibits a differential of 12. Consider yet another more complicated analysis scenario in which growth starts at an initial value of negative 8 and then reaches 16, also over a span of 25 milliseconds. Using the more comprehensive growth function, we can model this behavior as having an initial value, ai of negative 8, and a final value, af of 16, also with a time constant of 5 milliseconds. Substituting these values into the more comprehensive growth function yields y of t to be equal to 16 plus negative 8 minus 16 times e to the negative t over 5 milliseconds. Negative 8 minus 16 is minus 24, which leaves 16 minus 24 times e to the negative t over 5 milliseconds. Compare and contrast our two previous plots with that of growth from negative 8 to 16 over the same time span of 25 milliseconds. As one might expect, the growth from negative 8 to 16 is super abrupt, given it's lagging behind the others and exhibits a total differential of 24. all three plots still exhibit a characteristic growth curve shape. The initial value simply changes the differential that needs to be crossed in the same time period. The initial value, if you want to think of it this way, either gives the function a head start or holds it up. As a result, the growth function might appear vertically squashed down or stretched out. Using the more comprehensive growth functions, we can also solve for specific y and time values. Consider the function with an initial value of 4 and a final value of 16 and a time constant of 5 milliseconds, where y of t equals 16 minus 12 times e to the negative t over 5 milliseconds. Let's say we're being asked to evaluate it at t equals 5 milliseconds and again at 6 milliseconds. When t equals 5 milliseconds, we substitute 5 milliseconds into our equation. The ratio t over tau, 5 milliseconds over 5 milliseconds, is 1, meaning we're exactly one time constant into our analysis. E raised to the negative 1 is 0.368. 12 times 0.368 is roughly 4.4. 16 minus 4.4 is roughly 11.6. When t equals 6 milliseconds, we substitute 6 milliseconds into our equation. The ratio t over tau is 1.2, meaning we're 1.2 time constants into our analysis. E raised to the negative 1.2 is roughly 0.301. 12 times 0.301 is roughly 3.6. 16 minus 3.6 is roughly 12.4. Let's perform an analysis for these same times for a function with an initial value of negative 8 transitioning to 16 over the course of 25 milliseconds. Given an initial value of negative 8 and a larger differential of 24, we might expect these values to be different at the same times. Let's see if this is the case. This function could be modeled as having the expression 16 minus 24 times e to the negative t over 5 milliseconds. Let's again say let's evaluate this function also at t equals 5 milliseconds and again at 6 milliseconds. When t equals 5 milliseconds, we substitute 5 milliseconds into our equation. The ratio t over tau, 5 milliseconds over 5 milliseconds, is 1, meaning we're one time constant into our analysis. E raised to the negative 1 is 0.368. 24 times 0.368 is roughly 8.8. 16 minus 8.8 is roughly 7.2. When t equals 6 milliseconds, we substitute 6 milliseconds into our equation. The ratio t over tau, 6 milliseconds over 5 milliseconds, is 1.2, meaning we're 1.2 time constants into our analysis. E raised to the negative 1.2 is 0.301. 24 times 0.301 is roughly 7.2. 16 minus 7.2 is roughly 8.8. Let's compare and contrast the instantaneous values at 5 milliseconds of these two functions, one with a 4-unit head start, the other one starting at negative 8. At 5 milliseconds, the function in green has a value of 11.6. At 5 milliseconds, the function in purple has a value of 7.2. Can you dig it? At the same times, the function with a head start of 4 has a higher value and a shallower slope than the one with an initial value of negative 8. Coming at this from a different direction, at the same times the function with an initial value of negative 8 has a lower value and a steeper slope than the one with a head start of 4. This being said, both functions still reach 16 at 25 milliseconds. It makes sense. Finally, one can also solve for time values that satisfy specific y conditions. For example, given the expression y of t equals 16 minus 12 times e to the negative t over 5 milliseconds, let's say we want to know at which time value this function reaches 10, halfway between the initial value of 4 and the final value of 16. 10 equals 16 minus 12 times e to the negative t over 5 milliseconds. Solve for the t value that satisfies this condition. First, subtract 16 from both sides of the equation. Divide both sides by negative 12. Then take the natural log of both sides. Remove the negative sign from both sides of the equation and multiply both sides by 5 milliseconds. We're left with a time value of roughly 3.5 milliseconds. Let's try the same technique for the function with an initial value of negative 8. Let's say we want to know when the function y of t equals 16 minus 24 times e to the negative 2 over 5 milliseconds reaches 0 on the way up from negative 8 to 16. 0 equals 16 minus 24 times e to the negative 2 over 5 milliseconds. Solve for the t value that satisfies this condition. Subtract 16 from both sides of the equation. Divide both sides by negative 24. take the natural log of both sides. Remove the negative sign from both sides of the equation and multiply both sides by 5 milliseconds. We're left with a time value of roughly 2 milliseconds. Alright, put your understanding of the more comprehensive growth function to the test with this set of illustrated example problems. Let's say we're given a function that starts at 2 and grows to 12 over a span of 15 milliseconds. See if you can format this function using the more comprehensive growth function formula. Once you've got this function in the desired format, see if you can solve for the y value at t equals 4.5 milliseconds. Additionally, see if you can solve for the time value when y equals 10. The second example on the right features a function that starts at -5 and grows to 15 over a span of 300 microseconds. Obviously, these graphs are in different scales. As with the first example, format this using the more comprehensive growth function formula. Once you've got the formula in the desired format, see if you can solve for the y value at t equals 100 microseconds. Additionally, see if you can solve for the time value when y equals 0. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. For our first illustrated example, it looks like it has an initial value of 2 and a final value of 12, meaning it crosses a differential of 10 in 15 milliseconds. This time span represents 5 full time constants. 15 milliseconds divided by 5 is 3 milliseconds, meaning this function has a time constant of 3 milliseconds. The growth function formula would look something like this. Y of t equals 12 minus 10 times e to the negative t over 3 milliseconds. When t equals 4.5 milliseconds, we substitute 4.5 milliseconds into our equation. This yields an instantaneous value of roughly 9.8. Let's now determine at which time this function equals 10. 10 equals 12 minus 10 times e to the negative t over 3 milliseconds. Solve for the t value that satisfies this condition. One obtains a value of roughly 4.8 milliseconds. These results make sense. We demonstrated that the function obtains a value of roughly 9.8 at 4.5 milliseconds, and it seems logical that it reaches 10 a little bit higher, a little bit later at roughly 4.8 milliseconds. Our second illustrated example looks like it has an initial value of -5 and a final value of 15, meaning it crosses a differential of 20 in 300 microseconds. This time span represents 5 full time constants. 300 microseconds divided by 5 is 60 microseconds, meaning this function has a time constant of 60 microseconds. The growth function would look something like this. Y of t equals 15 minus 20 times e to the negative t over 60 microseconds. When t equals 100 microseconds, we substitute 100 microseconds into our equation. This ultimately yields a value of roughly 11.2. Let's now determine at which time this function crosses the horizontal axis and equals 0. 0 equals 15 minus 20 times e to the negative t over 60 microseconds. Solve for the t value that satisfies this condition. We're ultimately left with a time value of roughly 17.3 microseconds. Alright, that truly is it. No more curveballs, tricks, or bait and switch. In summary, you should have a good understanding of these two functions. Number 1, the general purpose decay function, y of t equals a times e to the negative t over tau, which starts at constant a and drops to 0 over a span of 5 time constants tau. 2, the comprehensive growth function, af plus ai minus af times e to the negative t over tau, which starts at an initial value of ai and grows to a final value af over a span of 5 time constants tau. The initial value ai might be positive, 0, or negative. As long as you keep track of signs, the comprehensive growth function works in all scenarios. Importantly, you should be able to solve for y values at specific times, and given specific y values, solve for the time value that satisfies this condition. Mastery of these analysis techniques takes time, practice, and discipline on your part, not to mention a reasonable background in mathematics. If you're struggling with later electrical concepts using these techniques, you may not necessarily be struggling with the electrical concepts, but rather the admittedly complex mathematics underlying these concepts. If this is the case, please feel free to revisit and review this lecture as often as you need to bring your math up to speed. Finally, you should have an understanding of the influence of tau and initial and final values. A larger tau value spreads the plot out as a function of time because the process is happening slower, whereas a smaller tau value compresses the plot as a function of time because the process is happening quicker. Regardless, all the magic happens between 0 and 5 time constants. For growth functions with initial values, you might notice a smaller differential squashes the plot vertically, whereas a larger differential vertically spreads the plot out. As wildly titillating as this lecture may have been, you may still be left with an important burning question. This question being phrased somewhat along the lines, when am I ever going to use this garbage? My answer can be found in this very quick example. We'll examine the electrical concepts behind these phenomena in later lectures. Consider a series circuit consisting of a DC source, a switch, a resistor, and an energy storage device known as a capacitor. A capacitor stores electrical charge on two plates separated by a small gap. In the uncharged state, no charge exists on the capacitor, and there is plenty of room for charged particles. The moment the switch is closed, current, moving electrical charges, rush in to charge up the capacitor. However, after the initial surge, current drops off and eventually stops. Quite obviously, current as a function of time can be modeled using the general purpose decay function. The instant the switch is thrown, current is some constant value and it rapidly decays to 0 over 5 time constants, where the initial current and the time constant are determined by the electrical properties of this circuit. Additionally, consider the voltage across the capacitor as a function of time. In the uncharged state, voltage across the capacitor is 0 volts. The moment the switch closes, however, charge accumulates over time and voltage builds and eventually stabilizes at some steady state value. Quite obviously, voltage across the capacitor as a function of time can be modeled using the growth function, in this case having an initial value of 0 volts. The instant the switch is closed, voltage starts growing to some constant value over 5 time constants, where the final voltage and the time constant are again determined by the electrical properties of this circuit. This is where we are going with these math skills, and if you don't have these math skills, you can't get there. I cannot make it much simpler than that. I could provide additional examples of the application of these functions to the transient or time-based analysis of discharging capacitors, building the magnetic field in an inductor, and collapsing the magnetic field in an inductor. However, I feel I'd be overwhelming you with much too much at once. Fear not, and rest assured that you'll be seeing these functions on a regular basis from now on. My hopes are that this extremely long lecture somewhat prepared you for all the math that is yet to come. In conclusion, this lecture presented the general purpose exponential decay and the comprehensive exponential growth function. We learned to calculate specific y values at given time values and time values that satisfy a given y condition. Additionally, we examined the influence of time constants and initial and final values. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.